All right, good afternoon, guys. So to start off this unit, we're specifically going to be working with exponentials. And so you've had a basic intro to exponentials in Algebra 1. So a lot of this stuff could be a little bit of a review, but a lot of it's going to be kind of new, and then we'll get into some deeper topics as we go on. But first off, just kind of looking at some basics of these exponentials and identifying some key features, kind of like we've done in a lot of our previous units. So for this first problem, what we're going to do is we're going to look at how we can identify the domain, range, the intercepts, asymptotes, and the end behavior of these exponential functions. So the first exponential that we're going to look at is f of x equals 2x. All right, and so just to get an idea of what the graph looks like, we're going to start off by making a table of values. So I want to take -2, plug it in for x. We have a negative exponent, so this is the same as 1 over 2 squared, which is 1/4. 2 to the negative first is going to be 1 over 2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. All right, so I'm going to go ahead and plot these on the graph just to give us a basic idea. -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. All right, so these are a few points, and we can kind of see how this graph is going up, and it's going up steadily, right? And so we could put a few more points on here at 3, 2 to the third is 8. All right, we can see how essentially each of these numbers is going to double. But one of the key features of this is not only does it double as we go up, but as we go to the left, it's going to half. And one of the things about that, though, is because it's going to half, this line is never actually going to reach 0. And so that's going to help us with some of our key features here in just a second. Okay, so that's what our graph looks like, and we'll start to identify those key features kind of as we go on. But the domain, essentially what we're looking for is we're looking for restrictions in the x value. All right, and there's no real numbers that I can't plug into x. So for the domain, we're going to say it is -infinity to infinity, or we say all reals. And it's going to be like that for all exponentials. The range, however, is affected, because if you look at the graph, we talk about the range as the y values, or bottom to top. And notice here the lowest y value on the graph appears to be 0. Okay, but remember how we said it approaches 0, but because these values are going to half, they're not actually going to get there. So we're going to put a parenthesis on the 0. We're going to say it goes from 0 to infinity. Another way that we can write this is just to say y is greater than 0. Not greater than or equal to, just greater. Okay. Next, we're going to look at our intercepts, where this crosses the x and the y-axis. And here, we can see that it's not going to actually cross the x-axis, but it will cross the y-axis at the point 0, 1. Okay, and the x-intercepts, there are none. Okay. The next key feature is what we call our asymptote, all right? And we've seen this before in previous units, but essentially what the asymptote is it a line that the graph approaches but never reaches. And so here, the asymptote is going to be the line y equals 0 for this particular problem. Okay. In behavior. Okay, so in behavior tells us the direction that the graph is going. So when I first look at this, we're going to look to see, all right, well, as the graph goes to the right, what direction does the graph go? Well, it's going up. So for my in behavior, we say as x approaches infinity, y approaches infinity as well. All right. Now, when we go to the left, it's a different story. Okay, see here how the graph approaches 0? So it's actually not going to -infinity like we've said before, but it's actually approaching 0. So for the end behavior, we say as x goes to the left, or as x goes to -infinity, y approaches 0. All right, so that tells us the end behavior of graph. Okay, let's look at one more of these. Okay, for b. All right, so this time our function is 5 times 1/2 to the x. So I'm going to do the same thing. We're going to start off with the table of values. 5 1/2 to the negative second. This negative exponent is only going to affect the fraction here. So this right here is going to be the equivalent of 5 times 2 to the second, which is 20. All right, with the negative 1, 5 1/2 to the negative first. The reciprocal of that is 2. So we have 5 times 2, which is 10. 1/2 to the 0 is 1. 5 times 1 is 5. 1/2 to the first is 1/2. 5/2 times 1/2 is 5/2. 1/2 to the second is 1/4. 5 times 1/4 is 5/4. Okay. So this time, when x is negative 2, we're at 20, which is way off the charts up here. At negative 1, we're at 10. 0, we're at 5. 1, we're at 5/2, which is 2.5. And 2, we're at 5/4, which is 1.25. Okay. So we can see that this graph is decreasing. And it's decreasing by half each time. So the same concept as before, whereas before we were exponentially increasing, this graph, as we go from left to right, we are decreasing. We are decreasing by half each time. So that same feature, because we are going down by 1/2, we're never actually going to reach that y value of 0. Okay. So looking at our key features, the domain, okay, we can write it either way. The range, this time it's going to 0, so we're going to say 0 to infinity, or y is greater than 0, either one. Intercepts, our intercept right here, okay, we can also identify the intercept when the x value is 0, right? Those both tell us that same thing. So my intercept here is 0.5. The asymptote. Asymptote is the line that it approaches but never reaches. Okay, and it's still going to be y equals 0. And in behavior, as we go to the right, where's my graph going? As I go to the right, the graph is approaching 0. So we say as x goes to positive infinity, y goes to 0. But if we go to the left, what's happening? The graph goes up. So as x goes to negative infinity, y approaches positive infinity. Right? All right, so those are just looking at some of those key features, and we'll see them in different types of graphs as we go along. So if you turn to the next page. All right, example 2, we're going to look at identifying just some basic key features. All right, and a lot of these are going to be familiar. We've talked about transformations of graphs this whole year, so it should be fairly simple. We're just applying it to a different graph. So before we do anything with the key features, I want to take a look at the parent function. So the parent function is going to look a little different for each graph depending on what the base of the exponent is. So we could have a 3 to the x, could have a 2 to the x, but it's going to look a little different for each one depending on what that base is. But for this parent function, y equals 3 to the x, we're going to take a look at what this graph looks like. So I want to show you, if you look at a calculator, one of the things that we can do I don't know if this is going to allow us to do it. I don't know if the light's going to allow us to. But one of the things that you can do is we can pull up a graph. Okay, if you put the graph in the calculator, you can look at the table of values and it will give you all of those values. So if I just want some nice points, okay, when x is -2, that'll be 1/9. This is 1/3. It's 1, 3, 9. All right, so y equals 3 to the x. Okay, we can see that basic graph. Now that's the parent function. Next, what we're going to look at is we're going to look at the transformation. So the transformed graph, you can see, has a negative out in front of it. And many of you probably already tell me what that's going to do to the graph. But let's take these exact same points and take a look and see what happens. Say -3 to the -2. All right, this is going to cause us to take the reciprocal of the 3. So we have 1/3 to the second, which is a -1/9. All right, so at -2, -1/9. -1, we have a -3 to the -1st. It's going to make that a 1/3. So we have -1/3. 0, we have -3 to the 0. 3 to the 0 is 1. With the negative, we have a -1. Right? So at this point, you can probably make that connection. Right? All it's doing is changing those y values to the negative version. Right? And so when we talk about transformations, right, when we have a negative in front of the function, we say that it reflects across the x-axis. Okay? All right. Okay. Once again, we have 3x minus 4. Most of you could probably already tell me what's going to happen here. I'm going to go ahead and sketch the parent function just so that way it's the same parent function, 3 to the x. All right, so I'm going to make a table of values just for us to get a visual. So at -2, so 3 to -2 minus 4. This is going to give me 1/9 minus 4. Right? And when I subtract these, you can do this in the calculator. I'm going to go ahead and do it by hand just this one time to show you. We need a common denominator. So 1/9 minus 36/9, it's going to give us a -35/9, which if I change that to an improper fraction, it's going to be -3 8/9. Right. So if we go down 1, 2, 3, and 8/9, you guys can probably see what's happening right now. Okay. Now, when x is -1, for the sake of time, and like I said, you can put these into a table of values in the graph, and you can get these points to see this. It's going to be a -3 2/3. When x is 0, it's going to be -3, 1, -4, 2, we end up with 5. Nope, sorry. At 1, we are not -4. I was looking at the wrong number. We get a -1. All right. Now, so one of the things that I want you to look at here is notice where the y-intercept is of the parent function, and notice where it is down here. That's one of the easiest things to look at, is identify the y-intercept and then look to see what happens in terms of those transformations. And it's clear that we can see that things have shifted down 4. Okay. Not only has the y-intercept shifted down 4, but look what happened to the asymptote. Parent function started at 0, and now the asymptote is down here at -4. Right? So it shifts everything in the graph down 4 units. Okay. All right. One more with transformations. Okay. Once again, g of x equals 5 to the x plus 3. Most of you guys could probably go ahead and tell me what happens here. Now, the parent function for this one looks a little different because it's our parent function is y equals 5 to the x. Not 5x, 5 to the x. So when x is 0, it's still 1. When x is 1 and we're at 5, 2, we're way at 25, so on and so forth. Right? It still takes the general shape, but some of your key elements or some of your points are just a little off. Okay, it's actually going to steep or increase a little more steeply. All right, so let's take a look at the table of values here. X is -3. So I'm using -3, and I'll tell you why here in just a second. So when we plug -3 in, we say 5 -3 plus 3 gives us 5 to the 0, which is 1. Right? So at -3, we're at 1. Already you can kind of see what's happening right here. This point is being shifted over. At -2, 5 -2 plus 3 equals 5 to the first, which is 5. So at -2, right, we can see it's being shifted over 3. Okay, and we didn't have this point way up here because it wouldn't fit. So sometimes if you have a graph that's being shifted to the left, right, we may need to try different points. So if let's squeeze in -4. 5 -4 plus 3, it's 5 to the -1, which is 1/5. Right? So we can see that this graph right here has been shifted left 3. Right? So all of the same transformations that we've worked with previously are going to apply to these same exponential units. Okay? All right. Okay, example 3. Example 3, we're getting into kind of some of the fun stuff, or the stuff that actually makes it seem like it's applying and we can use it a little bit. So example 3, we're dealing with models that involve exponential functions. So for A, it says the population of a large city was about 4.6 million, okay, in the year 2010, and it grew at a rate of 1.3% for the next 4 years. We're going to try to find an exponential function that models the population of the city over that 4-year period. And then we're going to compute so what we're going to do here is we're going to compute the population for the first few years by hand to find a pattern. Okay. So for year 0, I meant to put that in there. All right, year 0, that means 2010, population is 4.6 million. All right. After year 1, it is increasing by 1.3%. So to find that, we're going to take the 4.6 and we're going to add whatever 0.013 times 4.6 is. We're going to find whatever 1.3% of 4.6 is and add that to the 4.6. Okay, this will tell us what the increase is. We take the initial amount and then we increase it. Now, I want to show you another way that we can write this is if we look at this expression. Okay, and this is the way we're going to be writing it from now on. And this is just for me to show you how we get this. Is if we factor out a 4.6 from this, Notice how if I take a 4.6 away from this, we end up with 1. If I take a 4.6 away from this, I'm left with 0.013. So a simplified expression of this, of 4.6 plus 4.6 times 0.013, is 4.6 times 1.013. Okay. And we'll talk more about how that works a little bit later on. Okay. Now, year point 2, we're going to take that 4.6 million. We're going to multiply it by 1.013. And we're going to multiply by 1.013 again to get year 2, which this becomes 4.6 times 1.013 squared. Right? So at year 1, we end up with 4.6598 million. Year 2, we end up with 4.72 million. Right? And you can probably quickly identify the pattern. Every year that that's going to pass by, we're just going to increase the exponent. Right, so year 3 will be 4.6 times 1.013 to the third. Year 4 will be 4.6 times 1.013 to the fourth. Okay. What this allows us to do is, because we can identify this pattern, right, there's going to be a generic formula where P, which is the population, okay, is going to be equal to 4.6, which this is the population in 2010, times 1.013, which this is what we call the growth factor, raised to t, where this is the number of years since 2010. Okay. So I'm going to go ahead and introduce this now. We're going to use that here just down in part B. But we're going to be looking at two main different types of exponentials. We're going to look at exponential growth and exponential decay. Right? In growth is where we have the value in the parentheses that is greater than 1. In decay, where we are subtracting a rate, that value is going to be less than 1. But either way, these letters represent the same idea, right? A is going to represent the initial value. Okay, so like in this example right here, the initial population of the town when the exponential model started was 4.6. So that's the A. The R represents the rate of increase or decrease. In this case, the rate was 1.3%, or as a decimal, it was 0.13, which was added to 1. And T represents the time period. Okay. So, question B asks, if the population grows at the same rate, what will the population be in 2040? Well, we're going to take this model, P equals 4.6, 1.013. In 2040 is 30 years after 2010, where this model started. So we're going to put 30 in for T. We put that into the calculator, and it ends up giving us 6.777 million people. Okay. All right. So the next problem here, we have a function f of x equals 30 times 0.93 to the x. Okay, I'm going to go ahead and skip part B because the video's it's closing up on 30 minutes here. So what I'm going to do next is, because we were trying to find the value of the printer at 10 years, all we're really going to do is just take 10, put it in for x. We put this value into the calculator, and it gives us 14.519. Okay. All right. Actually, we'll go ahead and do this part. I'll just kind of give you some of the numbers. So the second part asks, if the printer loses more of its value in the first 10 years or the second 10 years? Well, the first 10 years we find by evaluating f of 10, which we just found at 14.519. Right? So the difference from the initial value of 30 to the value after 10 years was 15,481. Right? Well, actually, sorry, we're not talking. I'm assuming we're talking in thousands, but 15.481. If we find the value of the 3D printer after 20 years, which you take 30, 0.93 to the 20th, that's going to give us 7.027. So the difference from the initial value of the printer to 10 years is 15.481. That's how much the value dropped. But if I take the 14.519, the value at 10, and I subtract the value at 20, it only drops 7.492 in those next 10 years. Right? So with that exponential decay, okay, as it drops, it starts to level out. So as the years pass, that decrease becomes less and less and less. All right. Okay, let's go ahead. We got one more example on the back. Okay, and we will just do the first part. We won't worry about doing the second part here. All right. So example 4 says a car was purchased for $24,000. The function y equals 24 times 0.8x can be used to model the value of the car in thousands of dollars x years after it was purchased. Does the function represent exponential growth or decay? 0.8 to the x. So this value right here, this represents the initial value. Okay, that's what the car was worth. This value right here is our growth or decay factor. Okay, because 0.8 is less than 1, this tells us that it is decay. All right? If it was greater than 1, it would be growth. Part B says, what is the rate of decay? Okay, well, in the standard form for an exponential decay, y equals a 1 minus r to the t. Right? This 1 minus r, that represents the decay factor. This represents the decay factor. The r represents the actual rate. So what I'm going to do is I'm going to take 1 minus r, and I'm going to set it equal to 0.8, right, to figure out what that r value actually is. So I subtract 1, we have negative r is equal to negative 0.2, divide by negative 1, and r is equal to 0.2. Okay, well, what does it mean? The rate is 0.2. As a percentage, that is 20%. So what that's saying is the car value, decreases by 20% per year. Okay. All right, and I'll go ahead and close this off, and we'll finish up the rest of this when I get back next week. All right, good luck with your homework.